In this chapter, we will discuss a very important object, namely matrix inverse. Let me start with a very decent introduction. Consider the algebraic equation 5x is equal to 7. It is easy to solve this when we divide by 5 and we arrive at x is 7 over 5. And I will write this result in the form 5 to the power of minus 1 times 7. Absolutely clear. And this notation can be used even for a more complicated case. If we have a system of equations where we have more than one unknown and more than one equations, and when we have the same number of equations as the number of unknowns. That means if we have the system that can be described as A times X is B, where A is an n by n matrix, that means a square matrix, then in some cases we can immediately write the result as A inverse times B. And this A minus 1 is called the matrix inverse, and this is a very important matrix. Sometimes this is, however, not possible. If we go back to this trivial case, if instead of 5 we have 0 times x is 7, then no result, and something like this for 0 instead of 5 makes no sense. Similarly, for matrices, for some matrices the inverse exists and for some it does not. So that was the introduction. Let me give you the definition. We say A inverse, this matrix is the inverse matrix to the matrix A if the product is equal to E. E is the identity matrix, sometimes also denoted by capital I as identity, and it has the property that it has 1 on the main diagonal and 0 everywhere else, which can be schematically written as this way. For a 2 by 2 matrix, it is 1, 0, 0, 1. For a 3 by 3 matrix, it is 1, 0, 0, 0, 1, 0, and 0, 0, 1. So this is the definition, and if this is true, then we can multiply also in the opposite order, and this time we have the same result. So let me give you a few examples. If we have n is 1, that means 1 by 1 matrix. Well, this can be also written as a matrix if the matrix A has just one single row and one single column, and the entry is 5, then the inverse is 1 over 5. For if the entry is 0, the inverse does not exist. For a 2 by 2 matrix, let's consider some example 2, 3, 1, 1. And let me show you two algorithms how to evaluate, how to find the inverse matrix. So we want to find A minus 1 such that the product is E. That means 2, 3, 1, 1 times something, 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 something is equal to 1, 0, 0, 1. This equation between two matrices on the left and on the right is equivalent to 2 equations for separate columns. We can write it as 2, 3, 1, 1 times some unknown, namely this one, is equal to this column, and 2, 3, 1, 1 times, let me choose another color, which is this, should be equal to this. Well, and we can solve such a system of algebraic equations using Gauss elimination. And instead of solving this system alone and this system alone, we can combine these two computations into a single computation. Namely, instead of considering the augmented matrix and this one, we could combine, and then we use the Gauss elimination to bring this to the upper triangle form. We can combine this into a single large matrix, namely 2, 3, 1, 1. One column for the first system and another column for the second system. Actually, we write the matrix A, and then we write the identity matrix to the right. And then we use the Gauss elimination to bring this to the upper triangle form, and then the Gauss-Jordan elimination to bring this to the diagonal form. And then we divide to bring the left-hand part to the identity matrix. And when we do all the operations with the entire rows, then what turns out to be on the right will be the inverse matrix. So let me illustrate this for this matrix. So we have the matrix 2, 3, 1, 1 and 1, 0, 0, 1. So first we want to replace this one with 0. That means we copy the first row, 2, 3, 1, 0. And instead of this, we take the first row minus 2 times the second. Will be the new second row. 2 minus 2 is 0. 3 minus 2 is 1. 1 minus 0 is 1. And 0 minus 2 is minus 2. Well, this matrix is in the upper triangle form. And now we want to have 0 instead of 3. That means we copy the second row, 1, 0, 0, minus 2, 0, 1, 1, minus 2. And to get rid of this 3, we take the first row and we subtract 3 times the second. So 2 remains 2, 3 minus 3 is 0, 1 minus 3 is minus 2, and 0 plus 6 is 6. Now this is in the this left-hand part is in the diagonal form, and when we divide the first row by 2, we get the identity matrix on the left. 1, 0, minus 1, 3, 1, 0, 1, minus 2. Well, and this is the solution to the first system. That means the first column of the inverse matrix. And this is the solution to the second system, namely the second column of the inverse matrix. So we have the result that for this matrix, the inverse is minus 1, 3, 1, minus 2. We can check this. when we multiply A with what we believe to be the inverse, hopefully to get the identity matrix. Okay, let's do this. So the matrix is 2, 3, 1, 1. And we multiply by this matrix, -1, 3, 1, -2. So we have -2 plus 3 is 1, 6 minus 6 is 0, -1 plus 1 is 0, and 3 minus 2 is 1. And this is indeed the identity matrix, so it looks good. It means this is indeed the inverse matrix. And in the next session, we will see another method how to compute, how to evaluate the inverse.